Hello, this is Jose Luis here, and welcome to another hands-on exercise on the series Introduction to Parametric Modeling. For this exercise, we're going to practice a little bit of randomness as well, and also, in a way, we're also going to do a little bit of practicing of very controlled, very fine-grained randomness. Because what we're going to do is we're going to model a grass patch. We're going to model a patch of soil, of turf, whatever, that has grass sticking out of it. So what I would like to show you is how to take, for example, a surface and model these curves that look a little bit like grass that is growing tangent to the surface, but it ends up going in the pure vertical direction towards the sky. And I would like to show you a little bit how to add a little bit of randomness so that the tips of each one of these grass threads are not on the same level. It doesn't look like the grass was just mown, but it looks a little bit more uneven and give it a higher sense of naturality, if you will. But what I would like to show you as well is we're going to do this exercise in two parts. The first part is going to be the random distribution of the grass threads and the random heights, which is going to be super easy. And then the second part of the video is going to be showing you how to crank this up and how to do this kind of effect where the wind is going to be blowing through the grass, and it's going to create a super interesting effect of if we have a variable that is called time, about how the wind actually blows over this patch of grass with this kind of ripple wave effect, which I think is going to be pretty cool. Okay, and by the end of the video, or maybe on the next video, I will show you how to actually take this and animate this slider to create an animation that you can publish on your website, or that you can share with your clients, you can send to a competition, whatever you want to do with that animation. All right, wonderful. Without further ado, let's get started. As usual, we're going to start in the whiteboard and we're going to take a look at the steps that I think we're going to follow in order to make this parametric model happen. And I think in general, we're going to follow two very different stages. The first one is going to be modeling the grass patch. And then at a second level, the second stage will be taking what we have and then making sure that it oscillates as if the wind was sweeping over it. So we will first model it in a static way, so just the grass, and then the second phase will be the grass modified by the wind. So for the first stage, we're going to follow a fairly simple process, which is going to be, we're going to first find, where is my mouse? Let me first find my mouse, right? So we're going to first we're going to model a set of grass threads that are going to be popping out or growing out of a non-planar surface. We're going to imagine that we have some ground and then that the grass is growing out from it. And if we want to follow that logic, then what I would like to propose is a method that looks something like this, where the grass will kind of always grow out perpendicularly from the surface. If we have an uneven patch, I think vegetation typically starts growing out perpendicular to the slope where it's growing. I'm not sure that is actually botanically true, but I mean, for the sake of modeling, we're just going to assume that that's the case here. However, as the grass keeps growing, it's not going to keep growing in the direction of the surface. It's going to keep growing in the direction of opposite to gravity. So that's why I would like to model the grass in a way that looks like it's growing out of the surface, but then it's growing up towards the sky, if you will. In order to do that, and because we want to make it look a bit more natural, what I would like to do first is I would like to find a collection of random points on top of that surface. And as we already know, you already know me, those will probably not be points, it will probably be planes, because I would like to also know additional information from the surface, which is the orientation. So from those planes, I will probably take the perpendicular vectors and use those vectors to move the base points a particular amount along that direction, so that we use that second point as one of the points of the curve that we're going to use for the grass. And then that way we will have the intermediate point be kind of perpendicular to the surface. And then at a third stage, I would like to take all those points and calculate a vertical z vector that is not going to be the same for all of them. It's going to include a little bit of randomness because not all grass grows at the same rate, okay? And use that vector to create the third point that I will need to create a curve between those 3 points. And those curves will be the grass threads. Now, how are we going to move this with the wind? We will come back to that. That will be the advanced version of this exercise. But I think this part should be pretty straightforward. So let's go back to Grasshopper and see how can we implement this. All right, so let's start with the basics. I have created some random design surface, like a topographical surface, if you will, in Rhino, and I'm going to bring that surface into Grasshopper by dropping in an empty surface parameter component, right-clicking, setting one surface, and then selecting this one. I have also added a bunch of sliders, for example, for how many grass threads do we want, what is going to be the random seed. We have seen this in previous videos, and then some parameters for the geometry of the grass thread. So for example, how far away from the surface is going to be that point that we're going to define as the tangency, what is going to be more or less the total height of the grass thread, and how much variation is going to have randomly. So how far off are going to be some of the threads from each other. Now, the first thing that I would like to do as per our sketch is to find the collection of planes that is randomly distributed on top of the surface. And if you remember right from my previous video on this series where I was doing a landscape with random vegetation, what we can do is, in order to find random planes along that surface, is to create a set of random points from zero. It's like to find a set of random points on the surface. And in order to do that, what I can do is I can generate a series of random values from 0 to 1. So I can use the random component to generate numbers from 0 to 1. How many of those random numbers are going to be? We're going to generate as many as we have grass threads. And if you remember, with the seed of the random engine was going to be this one number that we determine to make sure that it's always, to make sure that the seed is controlled. And then if I do that, you can see that what I generate is a list of numbers from 0 to 1. How many? Well, 126, which is what I had here in count. And so those can be the U values of the planes on this surface. And if you remember, we also discussed how we wanted to create another list of random values from 0 to 1 for the V directions. But in this case, and the domain was also going to be 0 to 1, the amount was going to be the same. But in this case, the seed needed to be different from the previous one, because otherwise we would get the exact same list of numbers, and therefore all the points would be aligned on a diagonal. So that's why what we do is we take the seed, we add the value of 1, for example, so that we have another different seed, and then that way we have a different list of numbers. So if you can see here, now we have a different list of numbers from the beginning. If we had plugged in the same one, we would have gotten the same list of numbers. We use that to generate a collection of points which we will use as UV coordinates on the surface that we want to evaluate. So if we plug in the surface here now, and we make sure that this surface has been reparameterized so that the domain in each one of the directions is guaranteed to go from 0 to 1, then we can turn this on and we can see how we are getting a collection of a collection of planes that are distributed in a random way on top of the surface. These planes will now be the base for all the calculations that we're going to be about how the grass grows away from the surface. The next thing we need to do now is we need to calculate the second family of points. Those are going to be the points that are going to define the tangency of the root of the grass. So that's basically going to be taking all the points that we have on top of the surface, so the center of those planes, and moving them in a normal direction, a controlled amount. How much? Well, it's going to be however much we have defined with one of our parameters. So here, for example, the tangency of the root. So what I can do is I can say I have all these points, right, that are here when I deconstructed the planes. And I also have the c vectors for each one of the planes. So what I can do is I can multiply each one of the c vectors of the planes by the root tangency. And then just for the sake of visualization, I'm going to place here a display component for vectors. And I'm going to visualize these vectors anchored on the center of the planes. You can see that these vectors are going to be the ones that are going to define the tangency. And if I want more or less tangency, the only thing I have to do is I need to just change the slider. And then with this, then creating the second family of points is going to be as easy as moving all the centers of the planes by these multiplied vectors so that we obtain points that are away from the original surface. How much away? Well, right now, if I do 0, then they are going to be exactly on the surface, and if I do more, they're going to be more farther away. Okay? All right, piece of cake. And then the last thing is that now what we need to do is we need to figure out this family of points. This family of points is going to be perhaps a little bit more involved, but it's also going to be super easy because what we're going to do is we're going to take all the points that we just calculated, the ones on the root tangency, and we're going to move them in the z direction a controlled amount. How much? So much that in a way the total length more or less equals this parameter that we have defined, which is going to be the base height. So if the tangency is at more or less 3 units, then we need to move these points 7 units farther up in the z direction in the z direction, so that the grass more or less overall has a tan. We don't really need to be very precise here. So I'm going to subtract from 10, I'm going to subtract the value of 3. That gives me a 7. And then I can multiply that 7. I can multiply it by a c vector so that I get a c vector that is 7 units positive. And then I can just take all these points and then I can move them in the c direction, a controlled amount. If I now generate an interpolated curve, for example, if I generate an interpolated curve between the first points, the ones that are on the surface, the second points, the ones that are on define the tangency, and the third points, the ones that define the top, then I get this nest of points, which kind of looks cool, but it's not exactly what I wanted. And what have we said already? Whenever we have problems and whenever Grasshopper is not doing what we think it should do, what is the likely culprit? Who is probably guilty for this? We have probably some data problems. The data problem is going to be that if you look at the structure of the data, here what we have coming out is one single list with 126 elements, whatever. Then if we look at the second input, we have the same structure, and if we look at the third input, we have the exact same structure. If we mimic what's happening in this input by plugging in this panel the first one, and then adding with the shift the second one, and adding with the shift the third one, you can see that what we end up with is with a list of 3 times 126, which means that this component is trying to create one curve throughout the 300 plus vertices. And that's not what we want. What we want is one curve per 3 elements. So what we need to do is we need to graft this tree so that the structure looks something like that. We have one branch per element, and then we need to graft all the other ones. So this one here We also need to graft the third one here. And now when each one has that structure, you can see that when I merge them together, now I'm going to add with the shift here, and I'm going to add with the shift here. You can see that because they have the same branch names, when I graph them and add them together, each element is combined under the branch that has the same name, and therefore I have created lists, different lists that contain the base point, the tangent point, and the tip point. And as I do, if I plug this into here, now you can see that I have created all these grass threads. Sorry, I have created all these grass threads that are kind of, you can see they are growing perpendicularly out of the surface, but they end up getting straightened up to the vertical. And actually, I don't think, if you ask me, I think this curvature here doesn't look very natural to me, because I don't think grass goes back this way, and I think the problem is that we're using interpolated curves. So if we were to use control points instead, so let me try doing control points, just creating a NURBS curve, like a simple NURBS curve. I think it will give me a result that looks a bit more natural. So yes, this looks a little more natural to me. If we look at this, you can see that all the tips are now much more vertical. There's no weird curvature, but we still get the effect of growing, of kind of growing outside from the surface. And if I play with the tangency, you can see that little tangency, you see now all the threads are vertical. More tangency, you can see how the curves are now adapting even more to the surface, but they all end up very vertical, which I kind of like. So I'm going to keep, perhaps, I guess, like a larger, I'm going to keep something along these lines here. Okay. Now, what it doesn't look very natural is the fact that all of them almost look like they end up in the same place. They're basically replicating the surface geometry perfectly. It's almost like we have hairdresser come and like chop all the grass at the exact same height. And I don't think that's very normal. So what we want to do is we want to give this grass, we want to give it a slight variation. So what we want to say is, what we want to do is we want to say, let's say we had all the base points here at the same level, right? Because we had hard coded. What I want to do now is I want to make sure that each one of these has either randomly been increased a little or decreased a little, or increased a little or decreased a little, decreased a little, increase from the baseline. So what I'm going to do is I'm going to calculate a collection of random numbers that go from minus random grass variation. So for example, 2 plus grass variation. So if we say that the grass variation is going to be 1 unit, I want all these points here to go up or down a distance that is between the range of -1 and +1 randomly. So how am I going to do that? Well, it's going to be very easy. I have the random grass variation. So I want to create a list of random numbers. I'm going to go to set, sequences, random. And remember, the random asks me for the domain of the random range. So what I'm going to say is I'm going to create a new domain. I'm going to construct a domain that is going to go from negative, whatever this value is, to whatever this value is positive. So I'm going to do that, and then you can see that if I plug in a panel, I get now one single value. Now I need however many values, 120, whatever, and you can see that I'm now getting values between +1 more or less and -1 more or less. If I now take these numbers and I add them to the list of the base height, which we computed, it was the total height minus the tangency. If I add those two together, then what I will end up is with a list of random heights that are whatever the base was, 7, for example, I think we said it was, plus or minus random values between -1 and +1. And therefore, if I now use those as the c heights for the vector, you can see that now I have a stronger variation of the grass threads. Can you see that? And I can now play with that value. So if I set that to 0, you can see how now they're all aligned to the geometry of the surface. But if I crank that up, you can see now how I have a lot of variation between, you can see how I have a lot of variation between very short threads and very large threads here. Okay, so I'm going to leave this at 1.5, perhaps, maybe 2. I don't know. What do you folks think? Okay, so I'm going to leave that at 2, maybe, and that's going to be my. And I think with this, we already have a nice baseline, so I could already bake the curves here. I could group them and I could bake them, and then I could do like a little bit of whatever, and I already have this kind of grass that is protruding or growing out of my surface patch. Okay, which I think is kind of nice. Now that we have the base, now the next thing we're going to do is let's try to see how can we make this grass oscillate a little bit based on some hypothetical wind. It's not going to be very complicated. You're going to see it's going to be okay. Let's take a look at how it goes. So what we have right now looks something like this. We have 3 points, the base, the tangency, and the top, the tip, right? And we have a grass thread that goes through them. It's not really through because we decided to use a control points as opposed to interpolated points. So the thread actually doesn't go through the tangent point, but it doesn't really matter. But what I would like to do is to give it an effect that the wind is blowing over it. What I would like to have is some kind of control over where the tip is, and I would like that tip to be oscillating between two states, one that is like farther to one side and one that is farther to another side, for example, so that given a parameter that can be the time, whatever, blah, 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 then the grass is going to be oscillating between a maximum and a minimum. As you have probably imagined, anything that means oscillating between two states, it's typically implemented using some form of the sine or the cosine function, because it turns out that they are really good at given any value, giving you a value between 0 and between -1 and 1 that oscillates. So typically, this would actually be the cosine, technically speaking, because the cosine of 0 is 0. But for example, yes, so the cosine of an angle would be a graph like this, which means that, for example, if instead of thinking about the angle, what I think is about the cosine of time, as time goes by, when time starts at 0, the cosine is 0, so the grass thread would be at the rest position, if you will. Then as time goes by and we approach a time of half pi, then the oscillation would be maximum, which would be +1. And then as we keep going over time, we reach again an oscillation of 0. And then as we keep going, now we reach a value of -1. And then as time keeps going, we go back to 0, etc., etc. So if we take this point and we move it in one direction, a value controlled by the cosine of some number, this is typically an angle, but in this case, we're going to refer to it as time, because as we increase the time, the oscillation goes back up and down. So if we move that point to the left or to the right based on the cosine of time, then we will have this effect that we are looking for. Let's take a look at how to do that for all the points in my definition. So I'm going to remove this thing that I baked. I'm going to go back to ghosted, and I'm going to take this, exactly. And then what I'm going to do is I'm going to define a new parameter that I'm going to call, for example, time. And it's going to be something like this, for example. I'm going to call this time. And then what I'm going to do is that at any given point, I'm going to calculate the cosine of time, all right? And then the cosine of time is going to give me a value. For example, for the value of 0, the cosine is going to be 0. It's going to be 1. So it was actually the sine function. That was a big flop. So I'm going to do the sine function. The sine of 0 is 0, exactly. And then what I'm going to do is once I have my points, these are the points that I have moved in the x direction. Once I have those, what I would like to do is I would like to move them, for example, in the y direction, an amount controlled by this sign. So I'm going to create a unit y vector. I'm going to plug that in here, and I'm going to now take all these points and move those points, the ones that are the tips, I'm going to move them by an amount that is going to be the sine. And let's check out what's going to happen. As soon as I do increment the time, can you see how the points are moving back and forth as I change my time? And therefore, if I now use those points to generate the curves, what you can see is that all the points of the grass are oscillating back and forth, based on time. All right, how awesome is that? Now, this doesn't look very natural because when wind is, if you imagine wind sweeping through a field of wheat, for example, not the whole wheat doesn't move in the same pace. You can actually see these kind of ripples. You can see these kind of waves that are spreading over the wheat field. So what I would like to do now is I would like to improve this so that all the grass doesn't move at the same direction, but it moves on waves, if you will. Let's take a look at how to do that. Let's take a look at how to do that. Okay, bear with me with this one because I did a really bad job at drawing this on the screen, but bear with me. So remember that we had the sine function, and the sine function based on time made all the points move a little bit to the left or a little bit to the right, okay? Now they all move the same left to the right because time was the same for all of them, and therefore the sine of time was also the same for all of them. In this case, because we want all of them to move slightly different in this kind of wave ripple effect, what we need to do is we need to find a way to use the sine function, but in a way that each one of the points has a slightly different value for the sine of something. So what we can do is we can say, well, instead of thinking of the sine of time, what we can do is we can find a value that is slightly different for all of them, but in an incremental way. So if we think, for example, of a virtual wind point that is blowing from somewhere, and if we draw a line or a vector along all of the grass curves, then it turns out that we can find the distance from each one of those points to the original wind, to the center of the wind. And because that distance is going to be increasing, if we imagine plotting the value of the sine of that distance, we're imagining this. We're not going to actually do it, but you can imagine how for the value of the wind, for each value of the distance, the sine of the distance is going to be a value that is going to grow between 0 and 1, depending on how far away the points are. You see? And therefore, what that means is that for each point, when I calculate the sine of how far away that point is from the wind, then what I'm going to get is that each one of those points has a sign that is going to oscillate between -1 and 1. And then I can use that to move that point to the left or to the right, a value that is a factor of that -1 and +1. Okay? So let me show you that in the works. So what I'm going to do is I'm going to create a point. that is going to be, for example, it's going to be here. Can you see? Yes. So it's going to be here. And I'm going to bring that point into grasshopper. I'm going to create that point. And then what I'm going to do is I'm going to create a vector between 2 points. The first one is going to be the wind. And the second one is going to be each one of the tips. Each one of the tips of the grass. Not these ones. These are the ones that are amplified. It's going to be all of this. And for the sake of visualization, I'm going to use a display component that is going to be anchored on the wind point, and it's going to be using all these vectors. You can see that all these points are going to be, and you can see that time is something, you see, exactly. So you can see that these vectors are pointing to each one of the tips of the grass before the wind is sweeping. Now what I can do is I can take the length of that, vector. I can calculate the length. Actually, the length is already calculated here, so I don't even need to calculate that myself. So I can take that length and I can use that length to calculate the sine of each one of those values. And then as I do that, you can see that now when I move my points, the points get moved in a way that it's that some of them go back and some of them go forward. Okay, this is going to be difficult to see. You can see, for example, can you see if I move the surface a little bit? Can you see how some points move more than others? Can that be appreciated? It's very difficult to see, right? What if I crank up the amount of grass threads? What if I make this 1,000? Are we going to see that effect? I think we kind of see that effect. Can you see how there's like very 5 distinct groupings? This one, this one, this one. Can you see how there is a sort of distribution? There is like some more cluster here. And if I move this, you can see, if I move the surface, you can see how they recluster again. Okay, so this is starting to look good, but I think it's going to look even better when I do the following operation, which is going to be, because now this is static. And the idea is that I want to mimic the wind blowing through this grass. So each one of the grass threads has been moved by an amount that is equal to the distance. But if I want to make that dynamic, what I can do is, to the value of the distance, I can increase that artificially by another value that I'm going to call the time. And what time is going to do is that for every value of the distance, what I'm going to do is I'm going to be adding time to that value. What that is going to result is in the imaginary sine wave that I have on top of this. That imaginary wave is going to be displacing because I am increasing the value of distance by another value of time. So you can see how that would move to the right, and therefore each one of the points now is going to have an increasing or decreasing value of the offset for the tip. So that is just going to be as easy as taking the length that I calculated and to the length adding the value of time. And as I do this and I plug this into the sine computation, are you ready for this? It's going to be very cool. So what I can do now is I can, wait, let me zoom in here because it's very cool. What? Can you see the ripple effect? Can you see how there are this like wavy effect going on? Choo, 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 choo. How cool is that, huh? Alrighty. I think this is kind of, and what if the wind was coming from this direction? Wait, so that wind is going to come from the corner. So now you can see how the ripples are going to have you see, can you see how they're actually kind of, because they're forming like circles because it's, can you see those circles? Shoo shoo. And actually something that I don't like is that they're moving in the X direction. They're not respecting the direction of the, they're not respecting the direction of the wind. So now, and that was because I had hard coded here an unit Y vector. So what I would like to do is I would like to take the direction of the wind, which is this vector here, and I would like to make sure that the amplitude, I would like to create new vectors that are the same, but they have this amplitude here, the amplitude of the sine, and use those for moving. And then, as I do that, now you can see that now that the wind is actually what is blowing in the direction of where it's coming from. So like this one here, can you see now what? And if we look this way, you can see, can I choose a different visualization? No, this one is a little busy. Well, I can do that, why not? So I'm going to start, right? Whoa! How cool is this? Huh? All right. Well, I think that's where I wanted to get to with this exercise. Was this cool? Did you like this? Um, I think it's pretty cool, actually. I think it's pretty cool. Yes, I think that's where I want to leave this video, but I actually had a great idea because we have created a grasshopper definition that can kind of, by the variation of one parameter, show us a nice smooth animation. What I would like to do now is I would like to show you how to actually automate the generation of a series of screenshots that represent this animation, and therefore you can create frames for a GIF or for a video representing that animation. So, but I think I'm going to actually record a new video out of that, okay? And so I will, on the next video, I will explain how to take what we have right here and animate this slider to create a sequence of frames and turn those into an animation. So follow me out on that video. In the meantime, thank you very much. And maybe like this video, maybe follow the channel, maybe turn on notifications, all those things. All right, let's go to the next video and let's animate this thing and make a nice, cool video. All right, see you. Bye.